All right. So look, there's something to think about here that you guys need to come to a, I don't know, a come to religion moment, in that this is not your test for tomorrow. You guys understand that, right? That I can always sit out here in my porch late at night and come up with something new you've never seen. You have to come to a realization that it's not going to be this picture. It's going to be something new tomorrow, something that I haven't drawn or haven't put in front of you. So you need a method, and you need to have confidence that the method is not going to lead you astray. So I want you to think about a couple things about this. First, when it comes to question number 1, where I'm asking you about the possibilities of what could happen, friction is dependent on 2 things. First, it's dependent on how sticky the surface is. That's the coefficient of friction. That's the percentage. That one, is going to have to be given to you in some way, shape, or form. But the friction's also dependent on how much the 2 surfaces are pressed together. That's the normal force. If you've noticed, every time we've had one of these questions, I've indicated that the friction is a percentage of the normal force. So if you have a very small normal force, you're going to have a very small frictional force, no matter how sticky the surfaces are. And vice versa, if you have a small normal force, you can still have a lot of friction because the surfaces could be really sticky. So in this problem, when the object hits the rough patch, what happens is largely dependent on how sticky the surfaces are, because the object's normal force isn't changing before the rough patch and after the rough patch. The object's normal force stays the same until the kids jump on it. But the possibilities of what could happen, the ramifications of hitting the rough patch are the friction could be less than how hard you're pulling it, the friction could be the same as how hard you're pulling it, and the friction could be more than how hard you're pulling it. Those are the possibilities. A bunch of you focused on the results of those possibilities. Meaning a lot of you said this one, and it could be stopped. But saying that it could be stopped is talking about a motion variable, the velocity. And forces are all about acceleration. The only thing the forces can tell you is the acceleration. Once you have acceleration, you might be able to do something with that, but you're not going to be able to tell me whether an object stops or not by just knowing the forces. You'll be able to tell me whether it speeds up, you'll be able to tell me whether its velocity doesn't change, and you'll be able to tell me whether it slows down. That's acceleration. So in this problem, what I'm specifically looking for, and I even told you that there are 3 possible outcomes. I'm wanting you to recognize that there's the outcome where the net force equals MA, and this is going to increase the speed, where the net force is in the direction of motion. There's the possibility where the net force is equal to 0. And then there's the possibility where the net force is negative, which means that the net force produces an acceleration which is going to decrease the speed. These are the different possible scenarios. What does that mean? All right, if it increases the speed, the object's velocity becomes greater. It continues to move in the same direction. Net force is 0, the object's velocity doesn't change. It stays moving at whatever speed it was traveling at when it hits the rough patch. The net force is negative, the speed's going to decrease. The object's going to continue to move in the positive direction, but could come to rest. But it's at minimum going to slow down. Look, I can grade this one by just measuring how many sentences you write. I know right off if there's only one sentence written, you're getting 0 points. You can't possibly cover all of this. Why do you think I was able to walk around the room so fast? All I did was look at the first question and see how many lines were written. If there was one line written, you were wrong. Period. You couldn't have covered everything. When you're asked specifically to describe the different ways the frictional force could affect the motion of the sled, then you're being asked to describe the acceleration, the velocity, and the displacement of the sled. If you don't, you didn't answer the question. And then I was nice enough to go on and say, in your description, be sure to use the motion variables. So when I read yours, did you even use the word acceleration? Did you use velocity? Did you use displacement? If you didn't, you were not using the motion variables. And that brings us to the last piece. Saying stuff that just sounds right doesn't make it right. Our acceleration isn't speeding up and slowing down. Our velocity is. Our object could speed up and slow down. But you either have an acceleration which makes the velocity greater, or you have an acceleration which makes the velocity smaller. That's what you have. Accelerations are changes in velocity. So you need to indicate whether that change in velocity is making the velocity a bigger number or a smaller number. I mean, if you want a quick rule to memorize, if the acceleration is in the direction of the velocity, the object's speeding up. If the acceleration is in the opposite direction of the velocity, the object's slowing down. Heck, it could change direction and come back at you. However, friction will never turn an object around and push it back towards you. Friction always is just trying to stop the object from moving. Always. So it is going to reduce whatever is happening to the object. So that's question number 1. Is that nice and thorough? I'll take your silence as a yes. So let's go on to question number 2. One of the possible outcomes of problem number 1 is that the sled begins to slow down. All right? The child is already pulling with as much force as they can. They could change the angle at which they pull. Should they increase or decrease the angle? In your answer, be sure to explore what the effects of changing the angle would have on the forces and the motion variables. Now look, you can't get this question wrong as long as you explain it correctly. That's what's at issue here. Because we don't know enough about the problem to know whether you can get a specific answer. And AP is going to do this. They're going to ask questions where there might not be a single correct answer. They're looking for your explanation. Do you realize that if you make the angle smaller, you increase the normal force, which also is going to increase the friction? But at the same time, you increase the amount of force in the direction of motion. So what I'm saying is that consider that there's a finite amount of friction. So we have this frictional force acting, and there's this weight, and there's a normal force, and all of that is due to the fact that at the same time, you are applying a tension force in this direction. If I move the tension force here, then, then I am going to increase the size of the normal force. But I'm also going to increase the size of the frictional force. What you have to ask yourself is, does the amount that the sideways force that I apply increase enough to compensate for how much the frictional force is going to increase? And I don't have that answer. But the problem isn't about that. The problem is about you being able to say, if I make the angle smaller, I will increase the normal force and increase the frictional force. But at the same time, I will increase my applied force in the x direction. If I make the angle bigger, I decrease the normal force. I also therefore decrease the frictional force. I decrease the pulling force to the side at the same time, but it's possible and highly likely that my ability to decrease the normal force and the frictional force outweighs the fact that I lose a little bit of the sideways force. The answer to this question isn't a right or wrong answer. The answer to this question is, do you explain the repercussions of changing the angle correctly? And yes, the AP writers do this. They ask questions that are open-ended enough for you to explore the possibilities of the outcome. Yep. No, you would have to pick one and stick with it. So what I would look for specifically in a grading rubric, I don't have a rubric for this, it's a practice test, but in a grading rubric, I would say, does the person explain that changing the angle changes the normal force? And do they correctly predict how increasing angle decreases normal force for this circumstance? Decreasing angle increases normal force for this circumstance. Do they explain that changing the angle changes how much of that force is in the x direction? And do they do so correctly? Do they explain that changing the normal force changes the frictional force? Those are all of the things I would have on the rubric. So imagine this question 2, probably is a 6-point rubric, right? 1 point for you picking an angle change. 1 point for indicating how it changes the horizontal portion of that velocity. I'm sorry, that force. 1 point for explaining how it changes the normal force. And a couple points for explaining how the normal force is connected to the frictional force. That would be a pretty big build out for this problem. I think students forget to connect all the dots. And there's also the idea that no matter what you do to this force, you can't change this one by changing that angle. The weight is always going to be the same. There's plenty of problems I can ask where I just indicate the weight doesn't change and see if you understand that implication. All right. Anything else? Yeah. Okay. There's not enough information for you to be able to answer anything related to motion for this one unless you made an assumption. Like, because it says, what effects would changing the angle have on forces and the motion variables? The only thing you could indicate here, and this would have to be a conjecture, again, practice test. In this one, if you said that changing the sideways force reduced the frictional force so that you could have a net force in the positive x direction, I would assume you would say then that the object's velocity would increase because you were able to reduce the frictional force enough for your sideways force to compensate. So it would speed up. It would be on your test, yeah. But I'll be very clear. On your test, the question is more specific. So there's less opportunity for ambiguity. I was hoping that this question would generate conversation. Okay. Anything else, guys? Anytime. That's why my whole Wednesday nights are dedicated to all of you. I love a good night of sitting here on a Wednesday night and doing nothing but physics. After watching a good round of Chopped on television and eating some wings, it was nice. All right, somebody's talking. I have no idea who it is. I can hear you. Let's go with rough estimate. But don't get me wrong. If one of them is 400 and one of them is 100 and you make them the same length, that's not a rough estimate. I will expect that if you have information that specifically indicates you know the size of the arrows and you know which one is bigger than the other, that should be articulated. Does it have to be exaggerated or perfect? No, it doesn't. Nobody asked. I would be happy to go over number 3. So number 3, it says, the sled makes it successfully to point B where the ground becomes smooth again. A friend jumps on the sled, but the child can still only apply the same force as before, at the same angle as before. Since there is no friction, does the addition of the friend make a difference? Yes. Because in this situation before, the net force was unbalanced, which meant that my net force equaled MA. Now, yes, this part did not change because the person is pulling with the same horizontal force. The increase in the mass does change the normal force, but with there being no friction, there's no change in the frictional force. However, the inertia of the system is different. The system is now harder to accelerate because of the increase in mass of the system, which means the instant change in mass is going to mean a drop in the acceleration. The object will still increase its velocity, but it's not going to do so as quickly. So although it's still going to be getting itself faster and faster, it's going to do so at a slower rate and will take more time to speed up. So if you want to know how to answer this question correctly, you should address the fact that the acceleration is reduced. The velocity continues to increase, only slower, and the object continues to travel forward. How's that? So, you're welcome. All right, guys. Although I got like 6 people in the waiting room, I'm going to give, let's see, I've got Carlos is still here. Carlos, is there anybody else from your class here, or is it just you? Is there any other Monster students here? All right, so it is just you. All right. So, oh, hell no. He's his own man. Tell me the question and we'll work it out. Saying number 5 doesn't help me. All right, there you go. 15. Go ahead, say it. No, but you'll tell me again. What was the angle? What was the force? And what was the mass of the box? All right, so this is the exact same problem we just did. So here we go. If I want to know the acceleration of this system, I have to recognize that the net force on this system looks to be equal to MA. If I don't know for sure, I have to assume that. And I don't know for sure. So I'm going to assume that. I'm going to see how the forces behave. So judging by what I have here, I see a free body diagram with a downward force of 150 newtons. 75 is half of 150. So when I draw that 75 Newton force, I'm going to draw it to be about half the length. It's at an angle of 20 degrees, so a little bit's upwards. There's going to be a normal force that's going to be less than 150 because the 75 Newton force is helping. And there's going to be a frictional force that's about a third of the normal force. Why? 33. 0.33 is a third of the normal force. So I'm going to set up a coordinate system that is in the direction of motion, like so. And I'm going to recognize that my 75 Newton force needs to be broken up into both an x component and a y component. The x component, 75 cosine 20, which I have no idea what that number is. You'll need to do that. And the y component, 75 sine 20. Okay, so now I have two components of this force. I no longer need the force itself because they will stand in place of the original force. So now my net force in the x direction is equal to ma, and that's 75 sine 20 minus friction, and that equals 15a. Questions about that? Because the mass is 15. No worries. In the y direction, because I've decided to set my coordinate system aligned with the motion, the y direction is 0. It doesn't sink into the ground. It doesn't somehow elevate itself above the ground. So I'm going to have normal force, that's upwards. I'm going to have 75 sine of 20, that's upwards. And I'm going to have weight negative because it's downwards. Remember, add up all the forces. That's what that means. I'm adding them all up. I'm taking into account their direction. And then I set them equal to 0. Now, the last piece is you were told that the frictional force is 33% of the normal force. In my class, that's what I would say. Not till next week. Next week, I'll use the word coefficient of friction. But my class needed another shot at this test, so we're taking another round at it. So you need to find the normal force first. And then once you do, you need to, 33% of it is the frictional force. So everything you need to do is like right in front of you. You're going to find n. That's just a calculator. 150 minus 75 sine 20. Excellent. Don't make me wait too long. I got like 5 people in the waiting room. 25.65? That's the normal force? Can't be. Is that after you do the 33%? That I believe. 124 newtons. Yep, I believe that. So that means friction is 0.33 times 124. So that's like 31. But I'll wait for you. I'm sure Mr. Monster told you that friction is equal to mu times the normal force. So yeah. 40.92. So that's 41. Okay? All right, so now we got it all. 75 sine of 20 minus 41 equals 15a. That's how you get your acceleration. You're welcome. Does that help? Is that good? All right. You the man. You're welcome. Guys, this thank you. You guys, good luck tonight. Look, I'm not trying to trick you tomorrow. You know what I want you to do. I want you to do this stuff. Right? So you have spent an hour with me. I am sure you have done enough studying. Know the steps. If you know the steps, you're going to be fine tomorrow. If you want a little added bonus, know your motion equations. And focus on the first three. Those are the ones that I always use. Haven't you noticed? It's always either this one, it's that one. I use that one a lot. And I use this one a lot. I like that one a lot. And every once in a while, just for, poops and giggles, I like that one. That's it. If you know those three, you're golden. All right, guys, I'm going to kick you all out. I got the other 5 appearing in. So you two have a great night. Carlos, have a good night. I'll see you all tomorrow. Of course. Love you guys. You guys have a good night. The moment that's part of the problem, you're being told that this balance has to be maintained. Right? It says it's a static frictional force problem. So you need to maintain that balance. This is a constant. The normal force on the coin is the weight of the coin. So in the wall. That's weird because I can see it. No, I just think it's not updating anymore on the screen. So. All right, just chill for a second. I'm going to get my screen back going. All right, so there we go. So you already know that the normal force of the coin isn't going to change, right? It's the weight of the coin. So this side has got to be mu mg. Any question about that? All right, well, the frictional force has to act this way to keep the coin on the turntable as the turntable is spinning. Because basically what that really means is the coin has a tangential velocity and is on the turntable spinning in this direction. If I want the coin to be able to stay on the turntable, then the net force on the coin has to equal MAC. It's the only way the coin travels in a circle. This balance has to be maintained, or it doesn't travel in a circle. We want it to travel in a circle, and we want it to travel in a circle with a specific radius. Everybody here has a different radius. What is the unbalanced force that keeps it traveling in the circle? Friction. That is the unbalanced force that keeps it traveling in the circle. That has to equal mv squared over r. Still applying the rules. Add up all the forces, set them equal to ma. In this case, a is the centripetal acceleration. Now, they might want it in terms of the angular speed, so be flexible. If you have to give it in terms of like radians per second or rotations per minute, then why find the linear velocity when you can find the angular velocity instead? Now, I don't know what the problem actually wants, but I'm going to assume they want the angular velocity of the record. So I'm going to use this version. And I'm going to point out that that's the frictional force. So m omega squared r. Cancel the m's out. And I want to solve for omega. So omega has to be less than or equal to the square root of mu g over r. That's your answer. Whatever your numbers happen to be. This number is in radians per second, which is not RPS. RPS is interpreted by the problem as rotations per second. You need to type out radians per second for your unit, or you need to convert it to rotations per minute or rotations per second. If you did this, the answer is in radians. I'll tell you, I don't think you're getting the wrong answer. I think that it's going to be a unit issue. I could mastering. No, I guess I'll pull it up, but thanks. It's traveling in a circular path, so it has a downward force mg acting on it and an upward force of the normal force, which has to be greater because it's traveling in a circular path. Right now, the net force acting on it is equal to MAC in order for it to travel in that circular path. Now, I need to consider the fact that in the y direction, these are the two forces acting, but suddenly they slam on their brakes, which produces a frictional force in this direction. And the frictional force is proportional to the normal force. So I'm going to need the normal force before I can figure out the frictional force. So this represents the net force in the y direction, but the net force in the x direction is going to be equal to MAT, where t represents the tangential acceleration. And the only force in the x direction here is friction. So I need something that's going to give me friction. So I'm going to look to the normal force for that, which is going to give me normal minus mg equals mv squared over r, or normal equals mg plus mv squared over r. So if I make that substitution and that substitution, I'm going to get that, and I made the friction negative to indicate that it's slowing the car down. I don't really know how mastering is going to perceive that. But either way, that's going to be negative mu mg plus mv squared over r equals MAT. Cancel out all the m's, and mu is 1, so I get negative g plus v squared over r equals A. So whatever your numbers are, that's what I'd put in for that. You're welcome. I had to stop and think for a minute. Riley, Sana? Alrighty, I better pull it up because I already went ahead and got mastering running. So, alright, stump plane's going in a circle. That's not great. Let me try that again. All right, so the plane is maybe flying in this direction, and we are interested when it's going downwards, which is right there. And we are told, when I read this correct, that it's got an acceleration downwards right here. Mine is probably different than yours. Mine's 12 meters per second squared. But the fact that it's accelerating downwards and the fact that it's traveling in a circle means it's also got an acceleration this way. Now, the acceleration this way is based on v squared over r. The acceleration this way is whatever they give me. I have 12 meters per second squared. But the net force is going to be equal to ma total. There's two accelerations, one in the x direction, one in the y direction. So I need this acceleration, which is Pythagoras. If I get that, that's going to give me my net force. You're welcome. Is that enough? Excellent. Sana? Well, ultimately, there's two ways to go about thinking about this. The first is the unbalanced force has to be in the direction the object's velocity changes. So if you've got a car and it's going this way and you want it to go that way, then there has got to be a force that way. Because that force has to stop the forward motion of the car and create a sideways motion of the car. Right? Now, I don't care what that force is, but that has to be the net force. The combination of all the things that act on the car has to cause that force. So if I drill that down to just the instant the car's getting ready to turn, right here, that means that force starts by being this way. And then as the car turns, it starts to change. It becomes more this way, more this way, and more this way. That's why it's always seeking the center. That's why we call it the centripetal force, because it's the center pointing force. Now, that being said, the next thing about this is, well, what could possibly cause that force? When I start looking at the forces, is there a cable connected to the car? No. Is gravity doing this? No. Is there a surface pushing in this direction? No. The only thing left is the fact that if the car didn't have any friction with the road, there would not be a force causing it to turn. We all kind of know that intuitively, so the only thing left is friction. And that's not too terrible a surprise. We turn the wheels, right, to point in the direction we want to go. But the truth is we turn the wheels so that friction can act against the wheels, like the keel of a boat, to push on the car towards the center of the circle. Does that make sense? All right. Motion to change. That's what equals MAC. Or that's what equals MA. The idea that it's a combination of the forces. There has to be unbalance in order for there to be an acceleration. The fact that it's a centripetal or just a regular acceleration or both depends on the direction. But ultimately, the only way the object's velocity changes is if there's an unbalanced force. So when you're looking at the forces acting on the object, you have to include all of them. But the only one that can contribute to changing the object's direction is the one that's towards the center of the radius of curvature. So there can be another force acting on the object, but only the portion of it towards the center of the radius of curvature causes this kind of acceleration. If you're talking about the Earth question, then I don't know if you're overthinking it or not. The net force is what we're talking about there. If you're standing on the equator of the Earth is going in a circle. The only way you go in a circle is if the forces are unbalanced. And you can't get away from the fact that there are two forces acting on you. Your weight, which is going to stay the same, whether you're standing on the edge of the Earth or not. But the fact that you're in contact with the Earth means there's got to be a normal force. Those two forces work together on you. Now, if you want to go in a circle, then the combination of those forces has to equal mv squared over r or m omega squared times r. They have to, or you don't go in a circle. So this part has nothing to do with what forces are acting on you. That's what's required to go in a circle. And it has to point towards the center. So when I look at these forces, I see two of them. So I'm going to make towards the center positive, and weight minus normal has to equal mv squared over r. End of story. Now, what you do with that information is up to you. But that will have to be true. Does that answer your question? There is normal force. There's normal force in both cases. Because, yeah. Okay, what's the other? Then help me out, Emma. You know, 1/4 of the length. Oh, I didn't want to do that. That has to be 1/4 of the length of this whole piece down here at the bottom. Get that out of the way. So when I look at the size of that and the size of this, I'm comparing 400 to 100. Now, that being said, getting to the answers, which is, what we're going to want, you don't have to worry too much about it being to scale. You just have to make sure that what you have drawn clearly articulates the forces with an eye towards scale. It hits the rough patch. I need this whole thing again. But this time, the only thing that changes is now a frictional force is added to what's already there. And at this moment in the problem, I don't know exactly how much friction there is because I haven't calculated it. So whatever you draw here, you should just have an eye towards the fact that it is horizontal and perpendicular to the normal force. Yep. Yep. I think you should do that. Yep. Completely. Other questions? All right. So now we have to figure out what the acceleration is before it makes it to the rough patch, which means we're going to focus on this diagram because this is before it makes it to the rough patch. And a couple of quick things. If I'm worried about, what happens before it makes it to the rough patch, I don't really have to worry too much about the normal force or the weight because those two are balanced. I only have to worry about the horizontal forces. And in this case, because there's no friction, there's no force in the horizontal direction that has anything to do with the normal force. So I will take my tension force, break it up into two parts. tension in the horizontal direction, I'll use the cosine because it's the adjacent side. Anybody out there need me to do more triangle work than that? Alrighty. And then I'm going to draw it on here, but I don't need it for this problem. It's just so I can at least feel like I'm doing a bang up job of being complete. There's going to be a tension in this direction, a portion of the tension in the y direction, and this will be based on the sine of the angle. But I really don't need to do much here. The tension in the horizontal direction is 100 newtons times the cosine of theta, which is 0.866. So this force is 86.6 newtons. So let's actually go finish the problem now that I've broken my problems up into the x and y direction. To find the acceleration of the sled, I'll remember that this is a Newton's second law problem, so the net force in the x direction is equal to ma. I have a single force to the right of 86.6 newtons. That's going to equal m, which is 40, times a, my unknown. So a is equal to 86.6 divided by 40. And much to your dismay, I don't really care what the answer is. You can divide. So let's go to question number 2. No, it's because if I look at my set of steps that I gave you guys, the set of steps after I draw in my coordinate axis says to take all off-axis forces and break them into components. The weight's not off-axis. The weight points straight down. The force that is off-axis is the tension. It's the only one that doesn't point directly in the x or the y direction, so it's the one that has to be broken up into components. You're welcome. All right, so question 2 says, if the frictional force is 35% of the normal force, what will be the magnitude of the friction while in the rough patch? Good question. I think this is a reasonable expectation for your test tomorrow. So I look back at my picture now, and I'm looking at this one. And there's really not much of a difference between this picture and the one we just worked on. I mean, they're very much the same. So I don't really have to do the work again to break up the tension. I'm pretty sure that all of you will recognize that it's the same angle and the same size force. So there's going to be a force in this direction that's equivalent to 86.6 newtons, and a force in this direction that's equivalent to 100 sine 30, which is 50 newtons. Any questions there? All right, the weight is still 400 newtons. That's mg. The mass is 40, g is 10, so the weight is 400 newtons. So this is still a mystery, and that's what the question is about. So let's go check it out. Okay, go back over here. My net force in the x direction is ma. I don't actually know if there's an acceleration or not. And because I don't know, I have to leave it like that. And although that's the question for part 3, really, I always like to begin with the understanding of whether I know if it's a first law or a second law problem. So I'm going to stick with that in the back of my head, and I'm going to work on figuring out the frictional force. The frictional force, as told to me by the problem, is 35% of the normal force. This basically is the coefficient of friction, 0.35. Not going to be able to figure out the frictional force unless I know the normal force. So in the y direction, the net force is equal to 0 because I have a situation in which the object isn't accelerating upwards or downwards. So using this as my starting point, I look at the forces that point up in my picture, and they were normal plus 100 sine 30. And I subtract the forces that point downwards, 400, and set that equal to 0. So that the normal force is 400 minus 50, or 350 newtons. Questions? Alrighty then. Since friction is 35% of the normal force, right here, I'm going to take my 0.35 and multiply that times 350 newtons. And that's going to be the size of my frictional force, which, if memory serves, is like 122 newtons, I think. Somebody want to verify that number for me? All right, so that's the size of the frictional force. Going on to the next part, it says, what will be the magnitude of the acceleration while in the rough patch? Well, while it's in the rough patch, the net force is equal to ma. I have to assume that unless I know different, and I don't know different. There are only two forces that act in the x direction. There's that 86.6 newtons to the right, and now I know that there's a 122.5 newtons to the left. I have made the right the positive direction. And that has to equal ma. It's clearly not 0, so this object's going to accelerate. And it's clear that it's going to slow down because my net force is in the negative direction. It's to the left. And the sled in the picture clearly was moving to the right. So all of that suggests to me that we're going to have a negative acceleration. The mass here, that's still 40 kilograms. So when I plug that all in, I believe I get an acceleration of negative 0.89 meters per second squared. That's just a number. I don't care about the number. I mean, I do. It's easy to grade if the number's right. But you don't show this work, and Nathaniel, I'm talking to you, and I'm not sure you're going to get the credit. You've got to be able to demonstrate that you have an articulate flow of ideas. It's got to be there. So now we go on to part 4, unless there's any questions. No worries. I mean, I'm ballparking it, but just looking at it, the difference between 86 and 122 is almost 40. And I'm dividing by a number that is 40, so I'm expecting me to, around 1 or less. All right, moving on down to number 4. It says if two 60-kilogram friends jump on the sled while in the rough patch, these 60-kilogram friends, about 120 pounds. That's not too crazy. What will be the new frictional force, and what will be the new acceleration? All right. And then it says, will the sled slow or speed up? Look, there's no chance of it speeding up. Before it had the people on it, it was already slowing down. It's going to slow down more. But I want to be really clear. You didn't know that until you actually calculated it. It'd be really hard to know that answer before you calculate it. So this question, and I'm just letting you know, gives me the option to put 2 or 3 different kinds of tests out there, but make the questions all the same. All I have to do is change the weight of the sled. And I get some people whose tests have a test where the object speeds up, and some people who have a test where the object slows down. So just keep that in mind, that there might be more than one version of the test floating out there tomorrow. So, working this problem out, the only thing that changes is the weight of the sled. But that's going to reverberate through the whole problem. Because if I look right back up to here, that's where I found the normal force before. And the normal force was based on the weight of the sled. And that means the frictional force is going to change because it too is based on the weight of the sled. So when I look at this part of the problem, this number is going to go from 400 to 1600. Because I don't have a 40 kilogram sled, I now have a 160 kilogram sled. So taking that into account, I'm not going to do more work. I'm not going to redo everything. I'm going to say that normal minus 100 sine 30 minus 1600 equals 0. Because just because they jump on the sled doesn't change the fact that the net force equals 0. If the problem said that they jumped on the sled and the floor collapsed, no, then it doesn't equal 0 anymore. But as long as the floor doesn't collapse, the floor is going to continue to try and apply a force to keep the system from, accelerating up or down, which is going to produce a normal force, which is now equal to 1,550 newtons. That's just doing the math. So with that, I can find the new frictional force, because friction is going to be equal to 0.35 times 1550, which I don't know what that is. 500 and something probably, because it's about a third. Thanks, Adi. So I'm just going to put 543, but you guys should carry a couple of decimal places from part to part. It always works best, especially for like mastering and stuff. Now, the horizontal force hasn't changed. The person who's pulling the sled isn't pulling any harder. So the net force in the x direction is still going to equal ma. The positive force is still 86.6. But the force opposing that is now friction, is now 543. And that still equals ma. But here's where a lot of people make mistakes. It's 160 times A, not 40 times A. Because now that the friends are on there, their inertia is also making it harder to move the sled. So you need to make sure you increase the mass of the sled too. Saw a lot of that mistake today. However, I believe this comes out to be like 2.8 meters per second squared, and it is clearly negative. How we doing? We doing all right? All right. So now that we've gotten to this point, most of the physics is done for this problem. Question 5 is a motion problem, and they're the least interesting part of all of this. Am I going to throw it in? I've already written the test, so I really can't tell you. But I'll remind you that last time when we took the test, there were 2 of these in the multiple choice. And it threw a lot of you. So keep in mind that they're not particularly terrible, but I might be expecting you to do them really fast because they're on the multiple choice. So if you really want to make sure that you nail this kind of stuff and you want an A, make sure you know your motion equations. There's a couple of them on the equation sheet, but let's face it, I gave you the equation sheet to distract you. Right? There's like 50 some odd equations on there, and you only needed 3. So if you're spending any time at all looking on that equation sheet, it's time wasted. The only equation that you need for net force is F equals ma. And the only thing that you need for motion equations, well, your 5 motion equations. I'd commit them to memory and stop screwing around with it. The object started with an initial velocity of 3 meters per second. And it's going to slow until it stopped. I don't have to worry about B. I How fast will it be going after it's moved 5 meters? If it's speeding up, it is not speeding up. It is slowing down. I am doing only question A. The acceleration is negative 2.8 meters per second squared. I want to know how far it travels until it stops. And at this point, it should not take you more than a moment to recall what you need for that. That's why I recommended you commit it to memory. So you work that out. What are you going to get, like 1.6 meters? I mean, it's almost 3 squared divided by 6. So that's 1.5. I just gave it a little bit more. All right, so question 6. With the friends on the sled, is there an angle that the sled could be pulled with the same magnitude force that will allow the sled to move at a constant velocity? No, there's no frickin' way. Look, friction is 543 newtons. There is no way a 100 newton force could ever be great enough to compensate for 543 newtons of friction. On the other hand, should I give this test tomorrow and I'm telling you that you're pulling with, say, a 700 newton force? Well, that kind of changes things. It even changes things if I tell you that you're pulling with a 500 newton force. Because a 500 newton force might be large enough that if I pick the right angle, it will reduce the normal force enough to pull the sled. I won't be looking for a mathematical answer here necessarily, but just the idea that if the frictional force, say, is that long, and the weight, say, is, let's make sure you can see this okay. The weight is, say, this long. And I have a force I'm pulling with which is that long, but could pull in any direction I want. Is it possible that the normal force that I would get from one of those could be reduced enough to make the frictional force smaller? You have to understand, by increasing the angle, I decrease the normal force. And if I decrease the normal force, I decrease the frictional force. Now, it is also true that if I increase the angle, I decrease the amount of force pulling sideways. But remember, it doesn't decrease at the same rate. It's a sine function. So if I have the sine of 45 degrees, they're both reduced by just, 70%. That means they're pretty big still. So I just want to keep in mind that this question is less about the numerical answer and more about your ability to be able to say that you understand that changing this angle influences not only the frictional force but also the normal force, and can change how effective your applied force is. There's no football players in our little chat here tonight, I don't think. But if you are an offensive lineman, you're told to hit the defensive line low and push up at the same time. The reason is so that you can reduce their normal force. And by reducing their normal force, perhaps be able to push them back. So I want you to have this combination of ideas. The idea that if you can manipulate the angle of your force, you might be changing normal force and friction. All right. Adam, that's the second page. Are you still with us? All right. You had most of these answers because I popped in on your room when you were working it out in class today. So what are you looking for? Good. You're welcome.